Good afternoon, everyone. Today we're going to continue our discussion of machine learning with another algorithm. So far, what we have done is do a non-machine learning method where we computed for our model using the multinom from the GLM package, multinomial. So that's not really machine learning. This one, then we did decision tree using both the party package and the R part. And then we did a segue using FF3s, but that's for binary factors. Okay. Ours is multi-level, multinomial factors because we have three. Okay. So we said that a decision tree comes up with a model, okay, where we create nodes. And the nodes there would use only one variable, one predictor class. For example, LB is LB equal to like this. So that's a decision node. If it's yes, you go here. If it's no, you go there. So that's what a decision tree is. From the root class, from the root, you start with a decision node. Choose a particular variable of the variables that you're using for the model. In our case, we have three variables. We have three we call features: FEATURES, LB, AC, and FM. And we're using those three features in order to model whether the patient or observation is N or S or a P. Okay. Now, of course, we could have added onto the predictors. Adding onto the predictors class would, of course, reinforce our model. But this is just meant to be introductory. Okay, so we just use the three predictors or three features. Okay, so random forest class. It's like a decision trees in steroids. Because in decision trees, you only have one tree. You only have one model for the decision tree, and then you predict. You use your trained data set to create the model, and then you predict the test data set and come up with your confusion matrix to determine how accurate your model is. In random forest class, you can come up with 500 decision trees at the same time. Okay? And then you aggregate the result, come up with a more robust output class because you're using several trees at one time class as compared to just one tree. Diba? Doesn't it make sense, class? Your model becomes more robust, okay, as compared to just one decision tree. Okay, so an RF, a random forest, operates by constructing a large number of individual decision trees. That's why it's called a forest. Okay, now there's a good reference here. I just leave you to do that in your case study class, the one worth 30 points class. You look for good reference also and include that in your let's say in your output. Okay. All right. Now there are two things that are very important, class, as far as random forest is concerned, because you're coming up with random trees. So how do you come up with random trees? Two very important concepts which we're going to study now. I'm going to explain that. Let me illustrate that first, class. And then we go to the notes. Okay. Okay, let's start, class. How did we do our decision trees? Okay, if you recall, class, we had this one data, the cardio data set, right? And the cardio data set had 2,126 observations. Now we said that we're not going to use all of these observations. In our case, NSP, they're patients, right? So some are normal, some are suspect, some are pathologic. So once in a while, I'll be using the word patient. Okay, so this is a hospital setting. We said that we don't want to do overfitting. Overfitting is creating a model which is really tuned or really geared towards the data that you're using. So we're not going to do that because we don't want an overfitted data. Rather, we split our data into testing data set, training and testing, right? So let me call this our test data set. Test, and we have our train data set. These are train data set. Okay. All right. So how did we split this? Initially, we used the sample function, right? Sample function. And then we found out that the sample does not work that well as compared to the create data partition. The sample function will not be able to, say, preserve the proportion of your data, especially when you're dealing with classification. So in classification, you split your uh, target variable. In our case, it's our NSPF. And we found out that using the sample class will not really preserve the number of the levels of your or the classes. Create data partition from the caret package will do that. It will preserve the proportion of your classes. So we're going to use the train data set that we generated from the caret package, and we found out that there were 1701. And also it splits exactly. If you mention 80%, the sample will not do that. It will be more random. The create data partition will exactly split. So this was 1701 and this is 425. Okay. Now something happens with a random forest which does not happen with a decision tree. Okay, first let's take a look at the concept of bagging. So as the name suggests, bagging stands for bag. So imagine a bag, okay, where we put objects there. And the bagging here, class, is done using what we call bootstrapping. Bootstrap. Okay, bootstrapping is very important, class, because it allows you to generate more observations, more samples. Okay, so let's do this, class. Let's suppose we'd like to generate 100 decision trees. Okay, imagine, class, for a random forest, one set of code, you can generate already 500 decision trees or even 1,000 decision trees. Compare that with using package or RPart where you can only generate one decision tree. If you want another, then you have to create another model for that. Okay, so this is our, okay, so we're going to create 500, okay, 500 decision trees, class. So imagine these are your samples, class, and all in all 500. You'll have to have your data set, class, for your decision trees. This is decision tree number 1. This is DT number 2 until DT 500, class. Okay, how do we now create our sample data set? What we do, class, is to draw out from this train data set. So we get one observation first, put it in DT1. Okay, and let's say the observations here are numbered 1, 2, 3, 4. Remember, they're not really 1, 2, 3, 4. Okay, because some went to the test data set. But there are 1701 observations. Let's say the first observation that was drawn is observation number 5. Okay, so we take note of that, and we know that this observation number 5 we're going to use for decision tree number 1. This observation number 5 is, okay, figuratively or pragmatically sent back to your trained data set. So this is observation number 5 is still here. So we draw out another one, okay? And it's possible that we are able to draw out number 5 again, okay? Not necessarily consecutively, maybe as we draw on more, we'll be able to draw out number 5 again. Why is this possible? Because the drawing is with replacement. Replacement means we return that observation here, number 5. If it's without replacement, once we get number 5 is not returned to the trained data set. So that means there's no way for us to be able to draw out observation number 5 again. Okay, so this is with replacement. Okay, now how many samples are we going to get here? we're going to get 1701 observations also. So it's as if we're replicating our trained data set. However, the elements here, class, in decision tree 1 could be different now from the elements in our trained data set. Why? Because there's probability that we will be drawing out some observations n x number of times. Okay? So we have 1701 observations here now. Okay? We do the same for decision tree number 2. We draw out again. Of course, computer-wise, this can be done simultaneously because you can draw out from these 1701 observations at any time, any number containing all the observations here, and the number that you drew out can be again drawn out in future drawings. Okay. All right. So here we have also 1701 observations. Same thing, 1701 here. Same thing. So 500 decision trees with 1701 observations. That's what bootstrapping does, class. You can now generate out of one observation, out of one bag, 500 different bags. Okay? And each bag will most probably be different from each other. Okay? So that's what bootstrapping does, class, or in RF terminology, it's called bagging. Okay? Let me pause for a while, class. Did you understand that, class? Kindly comment yes or no, please, if you got that concept of bagging or bootstrapping. Okay, thank you, Moises. Okay, Paula, thank you. All right, good. I hope your comments keep on coming. Okay, thank you, class. All right, so what do we do with this now? Okay, but first take note, class, before we continue with the process. Take note that of these 1701 observations, some will not be taken in decision tree number 1. Okay, some will not be chosen because you have 1701 observations, and some will be chosen several times. Therefore, class, there are observations that will not be chosen in DT1. There are observations that will not be chosen in DT2, etc. And realistically, class, the ones that are chosen in DT1 will not be the same as DT2 or DT100. Therefore, the ones that are not chosen in DT1 will not be the same as the ones that are not chosen in DT2, etc., up to DT500. Okay, the ones that are not chosen in any bag class is called OOB. Okay, it's called out of the bag. So it's very graphic, no, out of the bag, which means it was not chosen in this bag or in this bootstrap sample. Okay, so clear, class, yung is the concept of out of the bag sample, class, clear? It simply means that these are the observations that were not chosen in a particular bootstrap sample, or in our case, it's our decision tree, the one that we're going to use for decision tree, number 1, number 2, etc. So there will be several OOBs, no? Different OOBs. Okay, is that clear, class? Again, another request for comment, for feedback. Okay, good. Thank you. How about the others? Yes, thank you. All right, good. Thank you, class. Okay, let's proceed, class. Okay, let's focus first on bootstrap number 1. Okay, how many observations, class? 1701. If you recall, class, in our decision tree, whether R part or party package, we use the trained data set to generate our model. And a decision tree model, class, will use nodes, right? Diba? Yung nodes na to. So the node we'll choose one variable, kunyari LB, class, LB. Okay, remember our model, by the way. Our model is an SPF. Okay, this is our factor. This is our target variable associated with LB plus AC plus FM. Okay, so decision trees will be choosing one of these class, either LB, AC, or FM. So for example, the model generated was, it first chose LB. So it asks, is LB greater than like this or this? If yes, then it will go here. If no, then it will go here. Until finally you come up with your decision tree for decision tree number one. Okay? All right. So you also come up with your decision tree for bootstrap sample number two or decision tree number two. So each of the decision trees here will have or could have different models. I'll explain in a while why it's possible for them not to have the same models. Okay, we'll explain why. Because you might be thinking, what if they have the same models? Diba? Kasi you have the same, well, number one, you have different data, right? But you have only LB, AC, and FM. These are only three. So it's possible that they'll be choosing LB first, and then AC, and then FM. If that's the case, then most probably you'll have the same models for all of them, or many of them. If they have the same models class, then this random forest will prove to be nothing because you're just having the same models. Okay, but later on I'll explain why it's very possible that the model DT1 is different from DT2 or DT3, etc. There's a sense of randomness in the model. Okay, so let me continue first class. So we now have a model for DT1, DT2, etc. We have 500 DT models class. Okay, now what are we going to do? Now notice in the regular decision tree, what we did was we now test the data for your decision tree. Okay, the complete one was, what we did was we have this model, and then didn't we create our confusion matrix for the trained data set? And then also, we said that the acid test is using the model for data that it has not yet seen, which is your test data set. And we came up with the confusion matrix for the test data set. Okay, and then we compared the accuracy. If in decision tree number one, okay, for the trained data set, the accuracy was 82%, and then in the test data set, it was 81%, then we say that then that's relatively okay because even if the model has not yet seen the test data set, it was able to create a model that was quite comparative with the trained data set, which it has already seen. Okay? All right. So I hope that's clear, class. Every decision tree will now have its own model. Okay. As I said, class, later on I'll explain why it can be very different models. It has something to do with the parameter mtry. I'll explain this later. Mtry. So just remember this, class. Mtry. All right. So let's go back to the OOB because the OOB class plays a major role, class, here. It plays a major role in the random forest model. Notice that I'm not going to use the test data set yet. I will have to use the OOB. So what's the OOB? Each decision tree has an OOB. Okay, so for example, for decision tree number one, we have OOB, let's say 2, observation 2, 10, say 21, 36, etc. Okay, so these are the OOBs for decision tree number one. For decision tree number two, it will have its own OOBs. OOBs are those observations that were not used in the bootstrap sampling and then in the generation of the model here, the decision tree model. Okay, so OOB1, OOB2, OOB3, etc. Okay, what will now happen? So, for example, we first take a look at observation number one. In what decision tree is observation number one an OOB? So we look for that class. Okay, let's suppose, remember class, there's a strong probability that your observations could be an OOB. You have 500 trees, okay? There's a strong chance that your observation will be an OOB for some of these trees. Okay, they will be present in some, some decision trees, some bootstrapping samples, but they will not be present in all of them. The probability for that to happen is quite small, okay? Because you are doing with replacement. Okay, so let's suppose that decision tree observation number one was OOB, let's say in 30 decision trees. Okay, so I'd like to pause class. I hope you got that concept na. So observation number one class, observation number one is an OOB for 30 decision trees. It means that in 30 of these 500 decision trees, it was not chosen. Okay, could you kindly please chat in the chat box if you got that concept, class? When I say the observation number one was an OOB in 30 decision trees, which means it was not chosen on those 30 decision trees. Okay, good. Thank you so much. Now, what are we going to do with those OOB with this observation number one? So let's say that observation number one is an OOB for decision tree number two. So observation number one is here. It's an OOB for decision tree number two. It was not chosen. And take note, observation number two has a model. Okay, so we're going to use observation number one here. Okay, and use model two class, decision tree number two, to predict the value of decision number one, of observation number one. Okay, what will be predicted class? Remember, observation number one is NSP, di ba? Lahat naman to, all of these are NSP. And we're going to predict whether observation number one is N or S or P using decision tree number two. Okay, remember decision number two has the capability already to predict because it generated the model using the values here, class. I hope that's clear, class. So we predict class observation number one in decision tree number two. Let's suppose that their prediction is N. Okay. So we go also to the other trees, class, where observation number one is an OOB. Let's say in decision tree number 500, observation number one is also an OOB. So we predict the model for decision tree 500. We predict observation number one. And let's say it turns out that the prediction of observation decision tree number 500 is an S. Okay. And let's say for the other observation, for the other decision trees, some are P's. Okay. So there are 30 OOBs for observation number one. Therefore, there will be 30 predictions. Let's suppose that N, the prediction for all these 30 decision trees, let's say all in all there was 11. Sa S there was, let's say 13. And for P there was 6. So this is 30, right? 30 predictions though. Okay, so that's what we're going to do for observation number one. And then this one, class, is compared. What's the actual value? What's the actual NSP of observation number one? Let's say it's S. It's S. This is the actual. And then we take a look at the predictions. Majority wins here. 11, 13, 6. So what happens is that 13 is the prediction for model number 2. And the actual value is S. Therefore, what can we say? The prediction was correct. Correct prediction. 13S here, and number one is actually S. So that's 1.4. So we have now correct and wrong. That's 1 point for correct. Okay. Then after we do it for observation number one, we will have to do it for observation number two. We choose the OOBs of number two, and then we again model it in those OOBs, and then come up with another like this. Okay. So you get the concept, class. You're going to do it for all the observations in your trained data set. Observation number one, observation number two, observation number three, number four, number five, up to observation number 1701. Okay, you can just imagine the computing power there, class. And in R and then in random forest, package, that's very easy. Okay, but you can just imagine behind the scenes what's happening. Okay, so it's not just one tree. Depending on your choice, you could have chosen 1,000 trees. Okay, so there will be 1,000 trees, 1,000 models. Okay, and there will be, let's say, B number of OOBs. There will be different OOBs for different observations. Okay, so all in all, class, how many predictions will be having? We will be having 1701 predictions of whether correct or wrong, because each of the observation here will be compared to the OOB predictions. Okay, you have the actual, and then you have your OOB predictions. So since this is classification, it's counting, class. It's counting. And my question is it possible for a tie? For example, this is 12, 12. Okay, that possibility is remote, class. That's remote. Okay, for some statistical reason. But in case that happens, class, one way could be to class to drop that, no? Drop that tie. That's one way. Or there's another way, class, but I'll not discuss that. But anyway, the probability that it will be the same is really very small. Okay, so what do we generate here, class? Let's say the correct ones are let's let's say, class, the correct ones are, let's say, 300. 300 observations are correct. Okay, and then so what's the wrong observation? 1,401 observations, predictions are wrong. Okay, so that's very, very bad. No? That's very, very bad prediction rate. 300 correct and 1,400 wrong, class. Diba? So that's only 300 out of 1,701 accuracy. And 1 minus, okay, and that's 1401 over 1701 bad prediction. Okay, so that will now be the role of the OOB predictions, class, because if the result of your first default random forest is bad, class, you can now fine-tune your model. Okay? You can now change, you can now tweak. Remember, class, dun sa ano sa tree control dun sa party package. That one you can do also for random forest. You can change. You can tweak it. For example, class, initially we used 500 trees, which is the default. No? This is the default. You can change it to 1,000 trees or 600, 700, etc. And try to see if you change it to n trees is equal to 700. Try to see if the model will improve. Will the accuracy improve? So if it improves, then that's good. It means that using more trees, 700, will improve your model, etc. So going back, class, what's the purpose of OOB? The purpose of OOB is for us to be able to fine-tune our data, our models. Okay, without going to the test data set yet, class. So take note that OOB is part of your trained data set. So in other words, we are at our disposal able to now validate our model using data that's part of our trained data set. Diba? Yun ang again, that's the advantage here, class. That makes the random forest really much, much powerful than just a simple decision tree model. Okay, so this is the goal in mind, class. Come up with an accuracy value using the out of bag samples. Okay, out of bag predictions. Okay, let me pause for a while, and once again ask, class, if you're okay so far with what we're discussing. Clear ba siya? Yung purpose ng OOB, out of bag sample, out of bag predictions. Okay, thank you. Thank you, Aidan. So waiting for the others to give their feedback. The good thing, class, is that you're not going to do that manually. It's the code that will generate that for us. It's the code that will generate the bagging. It's the code that will generate the bootstrapping. It's the code that will generate the OOB. It's the code that will compute for the accuracy. It's also the code that will hyper change the parameters, class. Okay, we just have to be familiarized with what the code performs, no? From the default up to the changing the parameters. Okay, in a nutshell, class, that's what happens with the random forest. So until such time that you're able to choose the final random forest, that's the only time you model your test data in your final random forest. Okay, same principle, class. The test data has not yet been seen. Okay, we're shielding the test data from creating our chosen model, chosen random forest model. So I hope you'll agree, class, that this is really decision trees in steroids, no? Okay, so we can come up with 1,000 decision trees and use the OOBs, the out of bag samples from your bootstrapping class, okay, and then use it to validate whether our model is good or not. Okay, so bagging allows us to do aggregation, class. We aggregate, class, and you use the OOBs, class. All right, so let's go to our notes, class. I want to discuss that because I want you to pattern that one, class, with your SVM. Okay, take note, take put your classmates in the context, class. How will your classmates benefit from the write-up of SVM, ANN, and XGBoost? Now, again, this is made in order for us to save on time and cover more materials. So anyway, it's an effort on your part, and you'll be rewarded with 10 points each for that. So I hope you come up with good write-ups, just like well, hopefully my claim is that this is good, will be validated by you. Of course, I noticed that there were some repetitions, which I think that it's okay to repeat the concepts, no? So let's now go here, class. All right. Random forest. So here. Okay, so let's now continue. Okay, so here, class, I'm discussing bagging or bootstrap aggregation. So we said that we create several decision trees, and each individual decision tree in the forest is trained, okay, on a bootstrap sample of the original training data. Okay, original training data, class, as I said, we use the training data, get samples out of that with replacement. How many? Same number, same observations as the number of your trained data set, 1701. So therefore, if we're creating 50 or 100 or 500 or 1,000 decision trees, we will have 1,000 bootstrap samples of 1,701 observations per sample. Okay, so that's how powerful, class, no? How powerful bootstrapping is. You're able to generate thousands of bootstrapping samples that we got from one bag, class. That's your bagging. So here I just said that there are 10 n observations in our data set. There are 1,701 observations from the trained data set. The bootstrap data sets that are created also have n observations each. Okay, I hope the language is clear, class. Anybody reading this will know that if you have 1,700 observations from your trained data set, your bootstrap samples will also have 1,701. Okay, so as I said, because you're sampling, we're doing with replacement, some observations might appear many times in a data set and some not. Okay, let's say you have B training data sets. In our case, we said 500, no? Yung B dito yung 500. Okay, we only have one data set, which is the training data set. Are we able to create 500? Yes, class. Yes. And that's the bagging, class. Bagging or the bootstrapping concept. Okay, so which we have just done. This is because each bootstrap sample is created by drawing n observations with replacement class. Okay, I want to, okay, with replacement from the original data sets of n observations. Okay, so the bootstrap samples have the same number of observations, but different combinations of original observations. Some repeated, some omitted. Okay, let me pause for a while, class. Is the language that I used here clear? Okay, do you find it, class, if you read this, class, do you find it easy to understand? Easy to understand, the class, or do you find it quite erudite? You find it quite difficult to understand? You just have to maybe read the sentence once, or maybe more than once. Okay, I hope I got the affirmative answer. Okay, thank you. Okay, thank you. Thank you for your feedback. All right, so let's, okay. This is what I said, class. Now, this is important, class. No? Statistically, we can show that if you do bootstrapping, class, it's possible that 36% of the original observations will be left out of a particular sample. Okay, 36% of that. So if you have 17,001 observations, maybe around, perhaps around, how many is that, class? How many is 36%? So 1701 times around, let's say 30%, that will be the observations that would most probably be left out. Okay, some of course less than 36%, some more than 36%. This is just an approximation. But there's a big chance that uh, that some of your observations will not be chosen in your bootstrap. Okay, so for each decision tree, the data that was not used to train that specific tree, aka the OOB sample, can be used as a validation set for that tree. What does that mean? We're now using the decision tree, which let's say decision tree number 5, and decision tree number 5 did not use observation number 2. So we're going to use the model of decision number 5, decision tree number 5, and predict observation number 2 using that model. Okay, so recall, class, that observation number 2 has not been seen by decision tree number 5. Why? Because it's an OOB, class. It was not used in creating the model. All right. So as I said here, each OOB estimation observation is passed through all the trees for which it was OOB. So again, observation number 1. You determine what are the OOBs for observation number 1. If there are 10 OOBs, then you create 10 observations for observation number 1 using the decision trees where it is an OOB. Therefore, you have 10 predictions. And then in those 10 predictions, you determine, is it the correct prediction or the wrong prediction? If it's the correct prediction, then you have 1.4 correct. Okay. Every time you have a correct prediction, you put it under correct. Every time you have wrong prediction, you put it under wrong. Okay. So how many predictions will we have? 1701, class. 1701, because each observation in your training data set will become highly probably become an OOB. Okay, so you have 1701 observations. Then, for example, you have correct observations 1,500, wrong predictions 201. Then that's quite high, class. Your accuracy has now become, so let's do that, 1,500 correct predictions divided by 1701. So that's 88%. Okay, 88% correct OOB predictions. Okay. So again, what's the purpose of the OOB, class? Okay, why don't we directly go to the test data set? Because the OOB, class, helps us in the hyperparameter tuning. We can improve the random forest model by using the OOB. Okay? The prediction from these trees are aggregated. Aggregated if it's classification because it's just added, and then average for regression. Okay, this aggregated OOB prediction is then compared to the actual value of the OOB. Okay, I hope you got this, class. Observation number 1 is OOB for 15 decision trees. We compute, class. We run the parameters of observation 1 in the decision tree, in this 15 decision trees. And then we count how many are correct, how many are wrong. Okay? And choose democratic vote, choose the best prediction. So the best prediction, let's say P is equal to, out of the 15, P is equal to 10. So P is the choice. And then you compare this P with the actual of observation number 1. If observation number 1 is also P, then that goes to the correct column. If observation number 1 is S, then that goes to the wrong column. Okay? All right, so there's a big advantage, class, in using OOB. It's a highly reliable and unbiased estimate. Why is it unbiased estimate? Because it has not yet been seen by your model. Okay? It's like a form of cross-validation. I'll explain this, class, next time. We don't have time to discuss this now. Cross-validation is different from bagging. Okay? But these are two, or bootstrapping, class. These are two types of generating different sets of data from your original data set. Okay? Cross-validation is quite different, and also your model can do that. So when we tweak our model, we can, because the default here is bagging for random forest, we can change, class, the process of creating samples by making it, instead of bagging, making it cross-validation. So cross-validation is quite different. Okay? But both are computationally efficient. Okay, because we don't, the bagging is also efficient because it avoids the need for explicit cross-validation. Okay, so remember, these are choices, class. Either you do bagging or you do cross-validation. Okay, now this one, class. I want to discuss this. We still have time. Random feature subspaces. Okay, so this is something to do with our predictors. Okay, let me discuss that, class. Okay, so our model, class, is NSPF. NSPF is associated with LB plus AC plus FM. And that's just include for our purposes of discussion. Plus FM plus there's DL plus DS plus ASTV, etc. plus MSTV. 1, 2, 3, 4, 5. Let's include, let's say, DSTV. Okay. So these are our predictors. No? Let's suppose we're using this model, LB plus AC plus FM plus DL plus DS plus DSTV. Okay. Now, how will decision tree be chosen? How will it be chosen, class? Because if you have this, class, if you use all of this, then the random forest will be able to see which of these ones is the most powerful. Let's suppose LB is the most powerful. Okay, so decision tree number 1 will choose LB as its first node. So here, first node niya, LB is LB greater than 120, for example. Okay, and so is decision tree number 2 also. Since we're using all of this, then decision tree will choose which is the best predictor, then maybe LB, and it will also choose LB. So if you have 500 decision trees, then what will happen is that there will be correlation because decision tree number 1 chose this first, decision tree number 2 chose that also, 3 up to decision tree 500, it chose this one, LB, greater than 120. Okay, so how do we stop this possible correlation? How do we generate randomness in the model that's being created? Okay, that is controlled by mtry. There's a parameter in your random forest function where you identify the mtry. And the default is that the mtry is square root of p predictors. So can somebody please get the square root of 6 here, 6 predictors? 6 predictors, please. How many, please? Paki-unmute na lang, please, kindly. How many, please? Square root of 6. 2 point what? Come on, class, please. Faster. Square root of 6, class. Why 6? Because there are 6 predictors. Okay, this is not the model class that we did, class. I'm just illustrating this. Because in our, unmute na lang, please, class. Unmute. What's the square root of 6, please?
2.449.
Thank you. Thank you. 2.4, around 2.45. Okay? 2.449. So around 2.45. So what will happen is that this mtry class will round this off to the lower one. It will become 2. And what's the meaning of 2 here, class? It has something to do with choosing the nodes, class. The nodes for your each of the trial, class, each of the node. So for example, 2 means it will just choose 2. So it can choose now randomly LB and AC. So let's say between LB and AC, LB is better to put in your node first to decide on LB whether it's greater than 120, etc. Okay? But take note, you're only taking it 2 at a time. So it can choose now DS and DSTV. The other decision trees can choose this one. So their model will be quite different from the choice of LB and AC. So your random forest model will choose randomly between DS and DSTV, or DL and DSV, DS, or AC and FM. It will go through this, choosing 2 at a time. And then remember that for your decision tree, only one node is chosen. Only one predictor is chosen. For example, if it's AC and FM, okay, 2 predictors. Why 2 predictors? Because your mtry is equal to 2. Your mtry is equal to 2. So it means you choose 2 at a time. Okay? So what will it choose? It will look at these 2 predictors and then it will choose the better one, let's say FM. Okay? So for another decision tree, it chose FM and DL, then it will have a different model now. DL and DS, DS and DSTV. So it will randomly randomly choose among these predictors. So that's why, class, it's not good to use mtry is equal to 6. That's a bad idea, class. What does that mean, mtry is equal to 6? You choose all the predictors. Okay? You choose all the predictors. So you choose between LB, ACF, MD, LDS, DSTV. And chances are, okay, the random forest model will choose the best one of them, let's say LB. And that will be true for all the other decision trees. They will start with LB. Okay, as I said, in order to prevent that, we impose this mtry is equal to either, so it's either 1, 2, 3, 4, 5, 6, up to 6, class. You cannot use, of course, mtry is equal to 7 because you only have 6 predictors. So either choose 1. So if you choose 1, then it will go to each of these, LB only. If you're only choosing LB, then of course that will be placed here. If you're only choosing AC, then you're going to put it here. So the default class is mtry is equal to square root of P, and then in this case, it's 2. 2.45 rounded down, it's 2. Okay, or you can use 3, of course, 3. So it will be 3 variables, LB, AC, FM, okay, or AC, FM, DL, or AC, DL, DS, etc. So you have different combinations, and that will now make sure that your models are robust and that it will prevent correlation. Okay. Again, class, feedback class, if that was clear, yung choice ng yung parameter na mtry sa random forest natin. Okay. Thank you everyone. Aiden, thank you Paula for sharing your answer. Okay, class. Clear yung concept ng ng randomness, class. Okay, good. Thank you, Moises. Okay, thank you. All right, good. Thank you so much, class. Okay, so I hope that how the a model is written helps class. How the process or procedure is written. Okay, let's go back now to what we have here. I'll allocate some minutes class for us to have our first uh, for us to run our first random forest. No? Because the rest class are just repetitions of what I have discussed. I just wanted to make sure that it is reinforced, it is repeated, so that you have really a good idea of what's happening. Okay, where are we now? Okay, here. Okay, we're now in the uh, where did we stop class? Okay. The advantages class, we said that's highly reliable. And then the feature subspace is this one. Okay, when growing each decision tree, at every split point, and take note class, it's only one node. You're not considering multi-nodes, no? Okay, I mean you're in one node class, you're only choosing one predictor. Not in one node you choose is LB greater than 150 and AC is less than like this and FM is less than like that. That's not how a decision tree works. You only choose one, okay, and then you propagate it, and then from this one, what's next? Let's say LB greater than 120. If yes, is there another node to consider? Or if no, is there another node to consider? If there's no more node to consider, then it will now go to the terminal node, as discussed class in what we have done. Okay, so the choice class of the variables, the features allow us to find the best split. Okay, it means that if a single feature, a single variable is very strong, it will not dominate every tree because that variable will not be chosen for every tree class because of the M trie, because of randomizing class the choice of the features. Okay, so the result is that there will be decorrelation among the trees. They will not be correlated because, for example, decision tree, the first node will be DL. For this decision tree, it will be FM. So there will be different decision trees. Okay, so by combining these two forms of randomness, which is the 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 bagging class and the OOB and also the M trie class, it will create a collection of diverse, relatively unbiased trees. Okay, so again, class, where is this one? Not again. Where is random forest used? Well, many applications, class, in finance, in marketing, in econometrics. I'll just leave you, class, to peruse over that. And then this is just a discussion again of bootstrapping. I just wanted to explain further, class. Okay. And then here, so random forest intrinsically uses bootstrapping as part of their bagging mechanism. Each tree is trained on a bootstrap sample. This internal process allows random forest to estimate out of bag errors. Okay, kasi some of the observations will not be chosen in your decision tree. Okay, and it's an example of cross validation. Okay, so bagging is an example of cross validation, but cross validation is different. The methodology for cross validation is quite different. So maybe it would be good for you to do some research class of about how cross validation is made, okay, in relation to bagging. What's the difference? What's the difference between them? So in this portion class, in this portion, what I did was to use our data, okay, to go through the process of the random forest. So our original data was cardio, and then what we did was to split it using the create data partition, 80%, 20%. So we now have okay. We're going to use now this 80% our trained data set to create bagging, okay, to create bootstrap samples. Okay, so step one already done. We use the cardio data set. We use the create data partition. So we generate the training data, 1701 observations, and the testing data, 425. Okay, this I know class you already understand because we have gone through this class. So I'm sure, and this is the process that I want you to do in your case, in your mini case. It's a mini case class kasi hindi naman kayo magmo-model doon. It's just a researching on how your three models class, three algorithms is done. Okay. And then this one class, the core process no, of random forest is create your decision trees. So depending on your n trees, n tree, number of trees, if you chose 500, which is the default class, then there will be 500 decision trees created. Each one having their own models. Each one has the ability to predict not only the data that they use, but also the data that they have not seen. Okay, kaya nga nakakapag-predict tayo ng OOBs class. Then we have this class, the bootstrap aggregation. Okay, each of these trees will be trained to classify observations and SP. So they will be generating their own models class, diba? Decision tree 1 model, decision tree 2, etc. Okay, and then what will happen is that we'll now have several decision tree models, DT1, DT2, etc. Okay, and then magkakaroon na tayo ng, by the way, in creating the model class, as I mentioned a while ago, we can, the default is the square root of P. No? If you have, for example, in our case, we have three predictors. So the square root of P there is the square root of 3. So that's practically 1 point something. So ang M try natin will be just 1. Okay, the default will be 1. So in order to determine the node, it will randomly go to each of the node, LB first, and then maybe FM, and then maybe, not necessarily LB first, no? Random siya. Maybe AC muna, tapos FM naman, tapos LB, tapos in another decision tree, another LB, etc. No? So ang ano lang na ano natin class, ang quote-unquote weakness ng model natin is that we only have a few predictors, tatlo lang. So it would be good for you to experiment class on what if you add the others, yung DL, yung DS, what could have happened to your accuracy? Okay, and then if you, let's say you chose 8 predictors, or you chose 9, no? So square root of 9, that will be 3. So the optimal is use 3. M try natin is 3. So 3 variables at a time. So iba't ibang combinations yun. And you can make it 4 class, no? Pwede ding 4. Or you can make it 5. Ang pinakapangit lang class yung M try is equal to 9. But you can choose that. But that will lend to, ang prediction ko class yung model where you use M try is equal to 9 will not be as good as M try is equal to 3. Kasi sa M try is equal to 9, R will now have the choice to choose among those 9 predictors. And if LB, for example, is the best, then it will choose it for decision tree 1, it will choose it for decision tree 2, etc., etc., etc. Okay, so here I mentioned class yung M try parameters and the square root class. Okay, and then in our case, P is the number of predictors, so that square root of P is equal to 3. Therefore, ang mangyayari dito class, at each split, the tree would randomly select only one of those 3. Saan nanggaling 1 class? Square root of 3 is 1 point something. So round down, it's 1. So even if it's 1 class, it means that it will go through all the choices, all the predictors. Minsan pipiliin si LB. Sometimes it will choose FM. Sometimes it will choose AC because it's choosing only one at a time. Okay? All right. So ito class, nagbigay lang akong discussion. What if your predictors is 10? So therefore, it will get square root of 10 class. No? Square root of 10 is 3 point something. So it will choose 3. So it will only choose at one time 3 predictors. Okay? DL, DPS, ASTV, or UC, DS, MSTV. So again, class, the algorithm will now force different models class. Kasi it will force the random forest to choose different different predictors for each node. Okay? All right? So I mentioned this class one node at a time. Okay? One node at a time and one predictor for each node. Okay, we don't use a multi-level categorical fixtures. Okay, it's not a multi-nodal approach. So for example, it's not a node, okay, can be split on FM greater than 20 or AC less than 50, or here class three variables are looked into. Okay, wait, a node can split only one at a time lang, either this one or this one or this one. So it cannot choose, it cannot split it FM greater than 20 and AC less than 50. It cannot do that, class, no? Okay. So I already discussed this, the use of mtry. Okay. All right. Okay, so I think, class, this one I have already described, class, no? You predict using the decision trees where your observation is an OOB, out of bag, class. And since we have 1701 observations for the trained data set, then we will have 1701 predictions of each of the observations, observation 1, 2, 3, etc., up to 1701. And then you count, class. You count the accuracy and determine if the model, if the random forest model is okay or not. All right? Okay, so I leave you, class. These are just similar. These are just, class, reinforcing what we discussed a while ago. Here, I just mentioned this, class. Okay, hyperparameter tuning. So once we have created the prediction for all the observations using the OOB, class, we use this in order to tune hyperparameters. Okay, so you have your R random forest model, class, with the syntax there. You can tweak the syntax. For example, class, entries, you can make it entries is equal to 100. You can make it entry is equal to 200, or you can make it 1000. It's really up to you. Okay. And also the mtry. There is the default. The default is the square root of your P, but you can change it. Okay. You can create a vector of mtries 1, 2, 3, 4, 5, etc., etc., etc. Okay. So again, pause another one, another pause, class. Oh, no. See, one last question, class. Did you get so far the whole idea behind the process of random forest? Kindly chat, please. Okay, good. Thank you. All right. I'll leave you, class, to read the other parts here. They're just the same, class. No? Example lang to, no? Example lang. Okay, we now go here, class. I already gave this to you. So set.seed, class, this is our default model. Let's create this set.seed. You can, of course, choose another number. And then we're creating this object random forest model. And in the random forest here, class, check nyo muna, by the way, class, no? I-library muna natin, class, yung run here. Sorry, I failed to control X dito. Put this here, class, before the default, no? Here, class. So caret, we have already loaded that. And random forest, if you haven't done that, please do that now. Okay, because this will only run if we load the random forest. Okay, so let's assume that you have already loaded random forest and, of course, caret. So if we take a look at this, the function is train, and then our model is NSPF LB plus ACSFM. We're choosing this, class, because we would want to compare it with our party and our decision tree models. Data is equal to train, same. The method is random forest. And then train control, class, TR control is equal to train control method is equal to none, which means, class, default to, no? Default. So whatever the train the RF model is class, use that. And then here class, about we create the prediction of train using the pred. The model is RF mod. Okay. New data is equal to train. Okay. And then we create the confusion matrix. The predicted value is RF pred train. And then this one is our compare it with our train data set. And then let's print this. All right, let's run this first class. Yung RF model natin. And you can see that our RF model is, sorry, RF model is a large RF model. R here. RF mod, no? It's a large train, similar to our part T or R part, no? The binary tree. Okay, so where are we? Okay, then let's predict now our train data set using the model, and then create our confusion matrix for the train data set, and then run this. Okay, so this is now our confusion matrix class. Now take note class that our reference is now x1, x2, x3. Hindi, it's not 1, 2, 3 anymore kasi in random forest class, it needs to be, we cannot use 1, 2, 3. That's the name of our levels class. It has to start with a letter. Okay, so accuracy class is 86.24. So this is higher than the 81s or the 82s that we created for our decision tree. Okay, it's better than no information class. Okay, that's statistically significant. Okay, and then you have here some other details which I said I hope you're looking at. Okay, and then there are explanations for this one. The train control method is equal to none means no cross-validation. Okay, just resampling is performed, yung bagging natin. Okay, and yung entry niya, entry is equal to entries, I mean 500. Entry is equal to the square root of b. Those are the defaults. Okay, and then you can take a look at the package itself and take a look at the documentation. No? Okay, here my documentation on random forest. Entry, ang default niya 500. Mtry class, yung predictors, how it will be chosen. The default is square root of p. Node size, for classification, it's always 1. For regression, kasi pwedeng 5. Okay, and there are other things here, class, that are the default. So what's important now is that we have created the OOB class. Okay, let's first take a look at our table class and see that our NSPF is now x1, x2, x3. Binago na siya ni random forest. No? Dati class in our decision tree, it's 1, 2, 3, right? Here, it's defaulted to include a letter at the start. All right. So let's print the levels of train. Here class, x1, x2, x3. And here class, the levels of train, make that names levels of train. So if you run this class, okay, same thing, it's the same thing class, no? Okay, so when we run this, what does it tell us? The default, 1701 samples, 3 predictors, 3 classes, x1, x2, x3. No pre-processing and resampling, none. Okay, so if we try to run this class, this one, RF default. Okay, so we now have this RF default, and then we print the RF default here. Okay, ito yung RF default natin class, no? And then let's, okay, it's already time, no? We can expand the grid class, yung try natin kasi, di ba? Ang default niya, square root of p. So it's only 1, 2, 3. We can change this into 1, 2, and 3. Okay, so How do you do that, class? Okay, hindi ko nalagay dito yung ano, mtry. Okay, this one, class, is this is now using cross-validation, no? 5 cross-validations. And then, okay, saan yung mtry claw? Okay. All right. I'm sorry, I wasn't able to put it dapat ano. So let me just change this, class, no? Kasi I forgot to put here the mtry, no? Hindi ko nalagay expand that grid dito. But anyway, class, this is also changing your parameters here. Yung train control natin, linagyan natin cross-validation, 5-fold. Okay? So, we define the control, and then we put it here, class. We said that the train control will now be equal to control. Ito yon, class, yung changes, no? Yung changes, so this one you have RF modified. Run this. You now have a new model, RF modified, class. And then you create a confusion matrix out of that, class. Okay, here. And, okay. Of course, class, please leave if you need to go, no? I'll just finish this. Ito na lang yung last point na to. So it's still running. And then if you run this, class, you'll find that the confusion matrix, okay, ito yung variance importance ng variables, class. Okay, we have this now, RF modified, and we tried to print RF modified. So ito siya, no? Notice na nabago na, class, yung ano, yung parameters natin. May resampling na, cross-validation 5-fold. So this is different from bagging. Okay. Summary of sample sizes. Okay. Additional sampling using S mode. And then you have here mtry, no? Sinama na yung mtry. Accuracy, if there's 1, if there's 2, if there's 3. You notice that the best one is mtry is equal to 79.95. And even the kappa, mtry is equal to 2 as compared to mtry is equal to 3. All right, so I'll leave this to you, class. Please do some, if you want, you can run the others, class. Okay, and then we have no classes next week, and I'll just post the requirement for the case number 3 and also your added case, which is the research on the 3 models. Okay, so let me stop recording now. Comment please, class, kung